I'm gonna solve some of the problems related to, I'm gonna focus here on force on a charge, a moving charge. When a charge moving, also when in a circular orbit. Also, I'm gonna focus also on a conductor that is carrying a current. Okay, now the first one is about a particle that has a charge of negative 5.60 nanocoulombs, is moving in a uniform magnetic field B that is negative 1.25 Teslas times K. The magnetic force on the particle is measured to be F equals negative 3.40 10 to the negative 7 in Newton I plus 7.40 10 to the negative J. First, calculate all the components of the velocity of the particle that can form this information that you can from this information. Are there components of the velocity that are not determined? That are not determined by the measurement of the force. Explain and calculate the scalar product V times F. What is the angle between V and F? Now, the first thing I'm going to do here is just if we can kind of make a... Oh, I don't have the... Oh, sorry. Come on, what I did. I did something that is not okay. This, I'm sorry, lecture again, going to chapter 27 here. Okay. What I want to do is I want to draw here. This is my X, this is my Y, and this is my Z. Okay, and what is going in here is that I have that particle that has this charge here. All right, and there is a magnetic the magnetic field. It is kind of lines that they are going to be in this direction, negative K, sorry, this way. Okay, then they are along the negative K, negative. All right, and then the force itself, okay, these are really, oh, yeah, let me represent these. Okay, let me do this. It's going to be much easier if I will do this. Okay, since it's going to be into the page, then my force is going to be this way. This is the force. Now, sorry, not the force, this is B. Okay, then this is B. And the force, it has a negative component of the X, then it's all right. For the X, it is negative. And for the Y, it is positive. Then I will say the force is going to be something like this, in this direction. All right. And of course, we are going to work with this problem. Here, B, it is negative 1.25 Tesla K. Remember the problem solving, we said, like, if you can put them in this notation, this is a very easy notation. And then here, I can say F, it is Q, V cross B. I want you to review, as was outlined at the beginning, the pre-knowledge, review the cross product, how we do the cross product. And here just to verify for you, when I'm gonna, like the force is gonna be Q, V cross B, then I, J, K, I will put the components for the velocity, which I will assume Vx, Vy, Vz, and then for the magnetic field, it is 0, 0. It doesn't have any X or Y. It has a negative Z value. And then now, okay, you cover like the first, okay, I will say highlight, just let me just highlight just to remind you. I will highlight this one. Then I will say I'm gonna multiply this one times this one minus this one times this one. And just I want you to review, and then I was able to find that it is negative 3.4 to the negative 7 in Newton I plus 7.4 to the negative n, I found this is really, these are the components of the force, I remember. Yeah, this is the components of the force. And this is the velocity here. I did calculate this here, the velocity. For the first one, I should do this here, okay? This one is gonna be negative Q times 1.25 Vy times I, and minus is gonna be plus Q. Okay, minus is gonna be a plus. Then and there is 1.25 again Vx, and that is J. This is the J component. And then when you compare these together, you're gonna find that Q times negative 1.25 Vy equals negative 3.4 10 to the 7. And let me write them here. Okay, minus Q 1.25 Vy times I plus Q 1.25 Vx J, and this equals negative 3.4 10 to the negative 7. All right, times I plus 7.40 10 to the negative 7 newtons J. And then when you compare these together, you will find that Q times negative 1.25 times Vy equals negative 3.4 10 to the negative 7 in Newton. And from that, I was able to calculate Vy as negative 48.6 meters per second. Also, when I compare the J component, I can conclude that Q times 1.25 Vx equals 7.40 10 to the negative 7. And from that, I will be able to calculate Vx as negative 1.106 meters per second. Now, here, of course, they are asking about which component will not contribute. Vz does not contribute to the force, so it is not determined by the measurement of F. Finally, they are asking us to do V times F. And if you remember, force is going to be always perpendicular to the both V and B. And you can do that, and it should give you a 0. But the problem is here, if you do an approximation like in the middle, then the number, you're going to get a number that is really very small, but it's not 0. But ideally, they should be 0. V dot F they should be 0, because when two vectors are perpendicular, you're going to get their dot product is going to be 0. Now, the second one, it's about flux. Then here, I'm talking about the most important concepts in this material. The magnetic field B in a certain region is 0.128 T Tesla, and its direction is that of positive z-axis in the figure. What is the magnetic flux across the surface A, B, C, D in the figure? What is the magnetic flux across the surface BE, like different surfaces? Now, if you look at the first one, A, B, C, D, this is this one, the one that is standing on the Z and Y. That one, if you look at it, and if you look at B, you are going to find that it is perpendicular. Okay, then it's just like it is, this one is Z and that one is on, standing on it, then it's going to be negative I, and then they are going to be perpendicular, and when they are perpendicular, then the flux is going to be 0. Okay, the reason it is when it is perpendicular is going to be 0 because the area is going to be out, going out of the, the surface, and then it is parallel to B. For BECF, like it's going to be on the other side, then theta is 180, and then negative BA equals negative 0.128 Tesla times the area, because the area it is 30 times 30 centimeters. You need to convert into meters so that we're going to get square meters. Then this is the negative 0.01152 Weber. Remember, this is the unit for magnetic flux. 5B is going to be, which is, of course, B dot A, BA, cosine theta, phi. This is the C, which is across AE, FD. AE, okay, then this is AE and FD. That is going to be making an angle which has a cosine that is 3/5. Okay, because we can find that angle from the dimensions, because we have this one is 5 and this one is 3, then you will be able to find the angle as 3/5. If we will calculate, this one is going to be plus 0.0115 Weber. If you will look at all the other surfaces, you're going to find that the flux is going to be 0. Then the total flux is 0, and that is really consistent with, when we calculate the flux over a closed surface, it should be 0. This one is about circular, the motion of a particle in a uniform magnetic field. I have an electron at point A. In the figure has a speed V0 equals 1.41 10 to the 6 meters per second. Find the magnitude and direction of the magnetic field that will cause the electron to follow the semicircle path from A to B, and the time required for the electron to move from A to B. Okay, here first, of course, we know that B should be perpendicular. Here I will say the force, the net force should be equal mv squared over r. And then here, that force, it is qvb sine 90 equals mv squared over r, because this object is moving in a circular orbit. Then I will be able to calculate B as 1.6010 to the negative Teslas. We know that the speed of that electron is constant. Then this is uniform circular motion. The electron is gonna make a total distance of pi r. Remember, the circumference is 2 pi r. Half of it is pi r. Then the time is gonna be the distance divided by the speed. And this is going to be pi r divided by v naught, which is 1.1110 to the negative 7. This one also talking about a motion of a charged object. Here I have 150 volt battery that is connected across two parallel plate, 5 square millimeters. We have alpha particles. Alpha particles, you need to know, we give them like alpha particles like this. They have a charge that is 2 plus 2 because they have 2 protons, and it has the mass of 4 protons, which is, you multiply, which is 6.6410 to the negative 27 kilograms. It is accelerated from rest through a potential difference of 1.75 kilovolts and enters the region between the plates perpendicular to the magnetic field as shown in the figure. What magnitude and direction of magnetic field are needed so that the alpha particles emerge undeflected? Then we're going to cancel the effect. Now, the first thing that we're going to do is we're going to say, delta K, or the change in the kinetic energy, equals Q times the potential difference. And here, of course, since the initial is 0, then I will say it is 1/2 mv squared equals Q times the potential difference. And from that, we will be able to calculate the velocity of the alpha particles when they're going to enter. Now, of course, these parallel plates, they're going to create an electric field that it is the potential difference divided by D. And from that, we can get what is E. And we know that the magnetic force should be equal to the electric force in magnitude and opposite in direction. Therefore, F magnetic is going to be QV times B and equals the F electric. Then the E is going to cancel and B is going to be E over V, and that is 0.0445 Teslas. This one is about conductors that they are carrying current. And here we have a long wire carrying 4.50 of current, makes 90 bends, like 90 degrees bends, as shown in the figure. The bent part of the wire passes through a uniform 0.240 Tesla magnetic field directed as shown in the figure and confined to a limited region of space. Find the magnitude and direction of the force that the magnetic field exerts on the wire. First, of course, B is out of the page as shown, which is plus Z. L, the length, it is, for the first one, it is 4, what's this, what I wrote here? Yeah, it has the same direction as L, it has the same direction as the current, but okay, this is not correct. Like, okay, why I wrote this? Okay, then forget about this here. Okay, F equals IL cross B, and then F, it is ILB sine theta. For all of them here, we have L and B, they are perpendicular, then theta is 90 for all. Now for FA, we're going to say ILAB is going to be 4.5, and we're going to assume that its length is X times the B. Okay, then this is I, this is LA, and that is the magnetic field. For FB, again, we can calculate it the same way. We know its length. But for A and C here, these two segments, we don't know. For FC, we know that it is I times LC, and LC, it is 60 minus X, and therefore is going to be the whatever, like 0.6 minus X, and then we are going to have that kind of expression for it. Now remember, here we have A and FA and FC are in the same direction, and therefore we can add them simply as we add numbers. And therefore they can be added, and when we are going to add, if you look, you are going to find that that X is gonna disappear. Okay, then because it is 1.0x and here 1.0x, 1.08x, and therefore we are going to have it cancelled, and therefore we are going to have the remaining term here is gonna be the 0.648 Newton, and the direction is along here. If we are going to look at it, is gonna be going down. What else now? Okay, now I will say here for B, the direction is going to be to the right. Therefore, I need to find, like I have two components. One of them is down and the other one to the right. I need to find the force, which is F square root of FAC squared plus FB squared. And I will be able to calculate the force and its direction. All right, two more, I think. The plane of a 5 centimeter times 8 centimeter rectangular loop of wire is placed parallel to 0.19 Tesla magnetic field. The loop carries 6.2 amperes current. What torque acts on the loop? What is the magnetic moment of the loop? What is the maximum torque that can be obtained with the same total length of wire carrying the same current in this magnetic field? Then here I will say the torque, it is I, B cross A, and therefore the magnitude, it is IB A sine phi. And that is really, remember, the angle is between the normal to the loop plane and field direction. And phi here, or theta, it is 90, and then the torque is going to be IBA, and like we can simply do that calculation. And the unit, it is in newtons times meters. The magnetic moment, it is I times A, mu, and it is 6.2 amperes times the area, and then 0.025 amperes times square meter. Now the maximum torque for that, if we are going to assume a different shape, is going to be the circular loop, and we can find the radius as the average of the like is going to be like, not that, what did I say, like what's the average? We're going to find that is going to be 0.05 plus 0.08. All right, and I will say A is going to be pi r squared, and from that we will be able to calculate the area and then calculate the torque. All right, and the torque, the unit, it is in Newton meter again. Oh yeah, this is the last one. Oh yeah, because I am in the, yeah, the other loops is in chapter, the other chapter. All right, then excellent. Thank you very much, and see you soon in another video.